Hello everyone, and welcome to Earth Archives. Did you know that there is a mysterious celestial object in the universe that even light cannot escape from, a black hole? It's not just a figment of science fiction, but a real gravity trap that exists in the cosmos. Want to know how black holes are formed? Why not even the speed of light can break free from their grasp? And what about the information inside black holes? Does it disappear forever? Today, we'll take you deep into the wonders and harsh realities of black holes and explore the universe's most profound secrets together. Don't forget to hit subscribe and ring the bell to join us on this journey to discover the infinite possibilities of the cosmos. Did you know that there is a mysterious celestial body in the universe that even light cannot escape from? That's our main focus today, the black hole. Don't think of it as just a fictional creation from science fiction. Black holes are very real gravity traps in the universe, incredibly powerful and awe-inspiring. Imagine standing at the edge of a black hole, trying to run away. No matter how fast you run, you can't outrun its escape velocity, a speed even faster than the fastest speed in the universe, the speed of light. In other words, even light is trapped, let alone us. How are black holes formed? Usually, it starts with a star much larger than our Sun. When this star reaches the end of its life, its internal fuel is exhausted, and it loses the power to resist its own gravity. As a result, it begins to collapse rapidly, eventually forming a singularity, an extremely dense and tiny point. This singularity is surrounded by an invisible boundary called the event horizon. This boundary acts like an impenetrable barrier. Once crossed, not even light can escape. Escape velocity changes with mass and distance. For example, Earth's escape velocity is about 11.2 kilometers per second, and the Sun's is even higher. But a black hole's escape velocity exceeds the speed of light, which is why light itself cannot escape from it. But if light can't get out, does that mean information is forever swallowed by the black hole? This is the core of the black hole information paradox. In the 1970s, renowned physicists Beaconstein and Hawking proposed that black holes not only have a temperature, but also emit radiation, now known as Hawking radiation, gradually evaporating and disappearing. However, this radiation seems not to contain the information about the matter that was swallowed, leaving scientists puzzled. Does information truly vanish with the black hole? Or is it somehow preserved? First, let's talk about why black holes trap even light. It all starts with a massive star, around 10 to 50 times the mass of our Sun. When such a star burns out and no longer has enough energy to counteract its immense gravity, it begins to collapse. You can imagine this star being squeezed tightly by an invisible hand, growing denser and denser until it becomes an extremely small yet incredibly massive singularity. This singularity is enclosed by a mysterious boundary called the event horizon. Any matter or light crossing this line is like falling into a bottomless pit. It can never escape again. This is actually one of the fascinating predictions of Einstein's general theory of relativity. This theory tells us that the greater the mass, the stronger the gravity, strong enough to warp the very fabric of space and time to an extreme degree. As early as the beginning of the last century, astronomer Carl Schwarzschild solved Einstein's equations to derive a mathematical model for such extreme objects, providing a solid theoretical foundation for the existence of black holes. Later, physicist John Archibald Wheeler coined the term black hole for these objects that trap light like cosmic pits, a concise and vivid name that was quickly embraced by both the scientific community and the public. Imagine trying to escape from just outside a black hole's event horizon. You would need to travel faster than the speed of light. But this is impossible in the universe because the speed of light is the ultimate speed limit of nature. So no matter how fast you move, light itself is tightly held by the black hole and cannot break free. That's why we cannot see the black hole directly, only the brilliant light emitted by the matter swirling and being pulled into it. This inescapable gravitational trap is one of the most mysterious and captivating phenomena in the universe. You might wonder, isn't light the fastest thing in the universe? So why does it get trapped? The key lies in the concept of escape velocity. Simply put, escape velocity is the minimum speed you need to break free from the gravitational pull of an object. For example, on Earth, a rocket must exceed an escape velocity of about 11.2 kilometers per second to leave Earth's atmosphere. The Sun's escape velocity is even more staggering, around 617 kilometers per second. But black holes are different. This gravitational monster has an escape velocity that exceeds the universe's speed limit, the speed of light. How is that possible? Imagine falling into a bottomless pit whose walls are pulling you inward faster than the fastest speed in the universe. No matter how hard you try to run, you simply cannot escape this pit. For light, this means that even traveling at its maximum speed, it cannot break free from the black hole's gravitational grip and remains trapped forever. This is the mysterious and harsh reality of black holes. Not even light can escape, making them the true dark kings of the universe. That's why we cannot directly see a black hole with telescopes. We can only infer their existence and properties by observing the radiation and accretion disks around them. The secret of this faster-than-light escape velocity is exactly what makes black holes both fascinating and baffling. However, the fact that light can escape doesn't mean we can't see black holes at all. In fact, the first-ever image of a black hole was captured by a powerful observational system called the Event Horizon Telescope. This is not an ordinary telescope, but a massive array of radio telescopes distributed across different countries around the globe. By synchronizing their observations over a long period, they were able to capture images of the hot gas and matter swirling around the black hole, forming a dark vortex that swallows light, revealing the silhouette of the black hole right before our eyes. So if even light can't escape, does that mean the information inside a black hole is trapped forever? This has been a major question sparking debates among physicists for decades. In 1972, Israeli physicist Jacob Bekenstein proposed a groundbreaking idea. The surface area of a black hole, specifically the area of its mysterious event horizon, is actually proportional to the amount of information the black hole can store. This surface area isn't like the ordinary area we imagine, but rather a quantum symbol of information storage. Bekenstein also introduced the concept of black hole entropy, suggesting that a black hole's entropy is directly related to its surface area, laying the foundation for later theories of black hole thermodynamics. This idea not only made us rethink whether information can truly vanish inside a black hole, but it also unveiled one of the deepest mysteries of the universe, posing revolutionary challenges to physics. 2 years later, Stephen Hawking shocked the physics community by discovering that black holes are not completely dark and silent. They actually emit a very faint heat radiation due to quantum effects, now famously known as Hawking radiation. Imagine it like a black hole slowly breathing, releasing tiny bursts of energy. Although faint over long periods, this radiation causes the black hole's mass to gradually shrink, eventually leading to the black hole evaporating and disappearing altogether. What's even more puzzling is that Hawking radiation seems not to carry the information originally held by the matter swallowed by the black hole. In other words, when a black hole fully evaporates and disappears, the information about the matter also seems to vanish, which severely violates the principle of information conservation in physics. This leads to the infamous black hole information paradox that has baffled scientists for decades. If the laws of physics tell us that information can never be destroyed, then why does it appear to vanish into thin air when a black hole evaporates? This problem struck like a sharp sword at the hearts of Hawking and physicists worldwide, sparking intense debate for many years. Hawking initially insisted that information truly disappears after a black hole evaporates. However, many quantum physicists firmly believe that information is an indelible part of the universe, and that the law of information conservation must hold. This contradiction is like a fierce battle between two superheroes in theoretical physics. On one side is Einstein's grand general relativity, describing the universe on a cosmic scale, On the other is quantum mechanics, governing the microscopic world. Both theories are powerful, yet when it comes to black holes, they clash in ways that have left physicists deeply troubled and searching for answers. In this theoretical battle, John Preskill, a theoretical physicist from Caltech, played a key role. He made a bet with Hawking over whether the information inside a black hole truly disappears as the black hole evaporates. The loser would have to give the winner a thick encyclopedia, symbolizing the ultimate cosmic mystery of whether information really vanishes. In 2004, at the International Conference on General Relativity and Gravitation, Hawking stunned the scientific world with a surprising announcement. He admitted that his earlier calculations were flawed, and his previous speculation about black holes producing baby universe branches was incorrect. More importantly, he stated that black holes do not cause information to vanish forever. Instead, the information is preserved within our universe. This shift disappointed many fans of scientific fantasies, as the dream of black holes as mysterious gateways to other universes seemed more distant than ever. However, this is exactly the beauty of science, constantly revising and pushing boundaries, with an endless quest for truth. Hawking's change of view reminds us that even great scientists alter their perspectives in light of new evidence and insights. Our understanding of black holes has evolved from absolute darkness and the loss of information to the possibility that information is preserved and somehow returned to the universe. This journey brings us ever closer to uncovering the deepest secrets of the cosmos. How exactly is information preserved inside a black hole? Hawking's view is quite fascinating. When you fall into a black hole, your matter and energy don't simply vanish. Instead, they are somehow represented in the universe in an extremely twisted and torn form. Only this information becomes so chaotic and scrambled that it's nearly impossible to recognize. In other words, the information doesn't disappear. It transforms into a kind of cosmic chaotic code, hidden deep within the black hole's radiation and scattered throughout the universe. This black hole information paradox is not only a huge challenge in physics, but also a major driving force behind the rapid development of quantum gravity theories and string theory. Scientists hope that by uniting quantum mechanics and Einstein's general relativity, the two great pillars of modern physics, they can discover a more complete and profound set of universal laws to unlock the ultimate secrets of black holes. Imagine a black hole as a gateway to the unknown, revealing the limits of our understanding of the universe. It is not only the most mysterious and powerful object in the cosmos, but also the frontier of humanity's quest to understand the laws of nature. Every breakthrough in our understanding of black holes could reshape how we perceive time, space, and information itself, and might even rewrite the entire story of the universe. Absolutely. Black holes remind us just how wondrous and complex the universe truly is, far beyond what we can imagine. These gravitational overlords of the cosmos trap even light with their astounding power, acting like the ultimate cosmic traps. The question of whether information is preserved or lost inside black holes isn't just a tough puzzle for physicists. It's a hot topic that sparks curiosity and passion among scientists and science enthusiasts around the world. Perhaps one day in the future, we'll finally unlock the deepest secrets of black holes and achieve a perfect unification of quantum mechanics and general relativity. That breakthrough would not only revolutionize physics, but also usher humanity into a new cosmic era, one that redefines time, space, and even the meaning of life itself. The mysterious veil of the universe awaits us, step by step, to be lifted. Black holes are not only the most powerful gravitational beasts in the universe, but also the ultimate challenge in physics and cosmology. From the event horizon to Hawking radiation, from the information paradox to the reshaping of cosmic laws, every breakthrough is awe-inspiring. If you enjoyed this video, please be sure to subscribe and share it with your fellow lovers of the universe and science. Also, Feel free to tell us in the comments which part of black holes fascinates you the most, or what other cosmic mysteries you'd like to explore. See you in the next episode. Let's continue exploring the vast universe together and uncover even more unknown wonders.